We're going to focus on solving complex equations and how we can make those complex equations easier for ourselves to solve. Every one of these 4 problems can be rewritten in an easier way before we try to solve it. So for example, in problem A, all of the parts have a multiplier of 32. So we could divide everything by 32, and all that would be left is the 3x minus 5 equals 7. And that's a much simpler equation to solve. In problem C, I noticed that every single thing is being divided by 3. So I could make this simpler if I multiply every single term by 3. And you can think of it as 3 over 1. Because what happens is when you have a divide by 3 and a times 3, they are opposites and they cancel out. So all that's left is the 1 plus x equals 10, those numerators. And again, we could solve for x by subtracting 1. 2 more examples. In problem B, all of these have a bunch of zeros. Those zeros are unnecessary. We could divide every part of this equation by the 3 zeros, so by 1,000. And so we'd be left with 9x squared minus 6x minus 15 equals, and 0 divided by 1,000 stays 0. Be mindful that this problem, due to the x squared, is called a quadratic. In order to solve this farther to get what x equals, you would need to either use quadratic formula or factoring. Similar to problem D, there's not something that can be divided by everything. But there is this decimal, 2.5. I'm not a fan of decimals, so what we could do here is multiply the whole equation, every single thing, by times 2 to get rid of that half. So when we distribute the times 2, we'd get 4x squared plus 8x and minus 5 equals 0. So without those decimals, it makes factoring or quadratic formula easier. We cannot complete the square because of the number in front of the x squared. You cannot have a coefficient there if you use complete the square. Here are some equations that have exponents. We're going to use a strategy called look inside. The symbol equal to means that they need to be the same. So when I look at this left and right side, I do see that the base number is a 2. Those are already the same or equal. 2 equals 2. So what I'm going to do is just look inside the exponent. I need the exponent on the left and the exponent on the right to be the same so that they are equal. So I can write them as the same or equal. That exponent x plus 2 equals 2x, or x plus 3. In your mind, you can think of that you just got rid of those bases because they were already the same. To finish solving for x, I can subtract x on both sides. So you get x equals 3 as our answer. We'll do a few more examples of this. Again, the bases are already the same. The bases are already equal, a 3. So I'm going to look inside these exponents because they also need to be equal in order to be the same. So we'll just look at 2x plus 1 needs to equal 3. So for x, 2x equals 2, divide by 2, and we get x equals 1. You could always check it by plugging back in a 1 as the x, and it would give you 3 to the third equals 3 to the third, which is true. In our last 2 examples, the bases are not the same, so we have to do an extra step to force these bases to be the same. What you are going to do is pick a number that is the smallest number that the base could be that could have an exponent to reach what you have now. So for example, 3 is a prime number. I can't use an exponent to change that number. But 9, I can change because 9 is the same as 3 squared. We need to keep the exponent that's on there of x. So we just changed the 9 to 3 squared, but we have to keep the x exponent that it had. And on our other side, we have the 3 to the 40th. Now the bases are the same, 3 and 3. So we're going to look inside those exponents and make the exponents the same or equal. To do that, reminder exponent rules, when you have parentheses, an exponent with another exponent, they just get multiplied together. So that makes 2x equals 40, looking inside those exponents. If we divide by 2, we would get x equals 20. You could always check your answer by plugging it back in. Does 9 to the 20th equal 3 to the 40th? You can do that on a calculator. And yes, it works. Another one like that. 2 is a prime number. I'm not going to change that base. I need to try to get 8 down to being a base of 2 with some other exponent. So I'm going to change 8 to match. It also has to be a base of 2. So I'm going to have 2's. 2 to the x didn't change, but how do I get from a 2 to an 8? I need an exponent. 2 to the 3rd power is 8. And we still have that exponent of 70. Now that our bases are equal, 2 and 2, we can look inside those exponents. Parentheses mean the exponents are multiplied. So 210 equals x. Oh, and that's done. You can check your answer. In a calculator, you can do 8 to the 70th and see, does that equal 2 to the 210th. So the goal is to take the base that is not a prime number and bring it down to match the base of the other part of the equation and use an exponent to get back to the same original number you had before. Our last type of solving is going to be a reminder of fraction busters. I'm going to start with problem C. When you're doing a fraction buster, you try to find the common denominator. In this example, the common denominator between 3 and 7 is 21. So I'm going to multiply the tops, or the equation, by 21 over 1, because that's the common denominator. Multiply every single term by 21. So if we multiply that through, we would get negative 42x plus 21 all over 3 minus 21x plus 63 all over 7 equals 168. That doesn't look like it helped us to multiply by 21. However, now these fractions can be reduced. 42 can be divided by 3 and 21 can be divided by 3. Now it's negative 14x plus 7 minus. This whole thing is grouped. Even though the parentheses aren't there, it's kind of a trick question. I'm going to do 21 divided by 7 and 63 divided by 7. So we're going to get 3x and 9 equals 168. To finish solving this, we can multiply by the negative or distribute this negative. Negative 14x plus 7, 3x is minus and minus 9. We can combine like terms and solve for x. Combine the x terms to be negative 17x. Combine the 7 and the minus 9 with the minus 2 equals 168. Add 2 on both sides. 170 and divide by negative 17. We get x equals 10. And you can check your answer by plugging it back in as the x. One more fraction buster. There's no need to get a common denominator here. There's only one denominator to the fraction, and it's in x. So what we need to do is multiply every term of the equation by x. So we're going to get 5x over x minus 2x squared, because it's 2x multiplied by another x, equals 3x. In fractions, the x over x cancels out. That was why we multiplied by x, to get rid of that denominator. So we have 5 minus 2x squared equals 3x. Right away, I see this x squared. So that tells me my only choices for solving this are quadratic formula, factoring, or complete the square. In order to use those strategies, we need to switch this to make the equation equal to 0. So we will minus the 3x. And I'm going to rearrange the order. So we've got negative 2x squared minus 3x and a positive 5 is equal to 0. And now we can pick complete the square, quadratic formula, or factoring. I think I'll pick quadratic formula because it works in all quadratic situations. So we've got the a, the b, and the c. X equals negative b, so positive 3 plus or minus square root b squared minus 4 times a times c all over 2a. Start underneath the square root, do that calculation first. Be mindful that when negative 3 gets squared, it's positive 9. And when negative 4 gets multiplied by negative 2, that becomes positive 8. So under our square root, we end up with 49. So I will just rewrite x equals 3 plus or minus square root of 49 all over negative 4. The square root of 49 is 7, and then we can solve this with two answers. We do 3 plus 7 and divide by negative 4, and then 3 minus 7 and divide by negative 4. So one answer is 10 over negative 4. I'm going to leave it as a fraction. The other answer for what x equals is negative 4 over negative 4, which is positive 1. So a reminder of the big idea: when you have fractions, you can look for a common denominator or multiply every term by the denominator.